And as the name suggests, you should think of it more as a general principle or idea which can be used in many different situations in slightly different forms. So let's just state it first and we'll look at many examples. So here's the principle itself. So let's abbreviate this to Pigeonhole Principle or PHP. So here's the principle in one of its forms. It says, suppose I have the following. Suppose I have n boxes. Okay, so think of this as n is some number and I've got n boxes. And suppose I have n plus 1 objects which I'm going to try and place into these boxes. So suppose I have n plus 1 objects. Okay, so I'll think of the objects as maybe like some balls or something like that. So I've got a collection of balls, but one more than the number of boxes. Then, no matter how you place these n plus 1 objects into these n boxes, the principle says there will always have to be one box which contains at least 2 balls. Okay, so observe there are many different ways of placing these objects into these boxes. For example, I can take all the balls, put all of them into a single box, or maybe I can split it half and half, put it into 2 different boxes, and so on. Many ways of doing it. So let's just number these boxes 1, 2, 3 till n. So the principle says no matter how you distribute, no matter how we place these n plus 1 objects into the boxes. Okay, so there must exist, no matter how you do this, there exists a box containing at least 2 objects greater than or equal to 2 objects. Okay, and observe, we can't say it will be exactly 2 because it is possible that we could have just taken all objects and put them just into a single box. So that possibility always exists. So let's restate this in a slightly different way. So here's another version of PHP. So PHP, let me just say another version. Okay, in which we imagine that the boxes are already filled. So suppose I have got n boxes. And I will again label them 1, 2, 3 till n. And imagine that each box has some objects. I don't know, maybe this has balls. This has something else. I don't particularly care what kinds of objects they contain and how many of each they contain and so on. So it's probably has some candy canes and so on. So the statement now says, given this situation, n boxes each containing some objects, okay, and some boxes can even be empty. Okay, so I will even allow that some boxes. Even be empty. So given this very general situation, and suppose I do the following, I pick or take n plus 1 objects from these boxes. If we choose n plus 1 objects from these boxes, in any possible way, you may pick lots of objects from one box, a few from another, nothing from some other box, and so on. But no matter how you do this, as long as you choose n plus 1 objects from these n boxes, you will have to choose at least 2 objects from some box. Okay, these boxes, then there exists a box from which we must have chosen two or more objects. Okay, so that's just another way of stating, in a sense, the same principle. Now, let's look at yet another version. So sometimes this is a slight generalization of PHP, if you wish. So, Pigeonhole Principle. This is sort of other version 3. So the previous version is version 2. So what is the slightly more general version? It says, so again, so this starts from the first version. So I have n boxes and I'm trying to place objects into these n boxes. Okay. Now, how many objects do I have? Earlier I had said in version 1 of the PHP that I've got n plus 1 objects. Here, suppose I have not n plus 1, but let's say 2n plus 1 or 3n plus 1 or generally some kn plus 1. Okay. So I have kn plus 1 objects where k is some number which is 1 or more. So I take a multiple of n, kn, and I add 1 to it. So suppose I have these many objects which I now have to place into these boxes. Then, so here's the principle: no matter how we place these kn plus 1 objects into these n boxes, there must exist a box containing at least k plus 1 objects. Okay, so observe that the first version of PHP was really the case when k was equal to 1. So in that case, I was having n plus 1 objects, and I concluded that there is a box which has at least 2 objects. So let's prove version 3, which says that if I somehow place kn plus 1 objects into n boxes, then some box must contain at least k plus 1. So let's try and prove this by, let's say, by contradiction. So let's prove by contradiction. And recall, what does that mean? When you try and prove a statement by contradiction, you assume that what you have to prove is false. Okay, so we will assume that the conclusion does not hold. So what does this mean? In other words, i.e., that all boxes contain, so remember the conclusion was that some box contains at least k plus 1 objects. What is the opposite of that? What does it mean to say that does not hold? It means that all boxes must contain k or fewer elements, at most k elements, k objects. Okay, now how many boxes did we have? There were exactly n boxes, okay, which implies that total number objects is, well, how many? There are n boxes, each containing k elements. So this is n into k, so at most k times n. But that's a contradiction because we assume that we had kn plus 1 objects to begin with. Okay, so this contradicts given hypothesis. We had kn plus 1 objects to begin with. So that's the end of the proof. Okay, so proved. Now, I mean, this is a fairly intuitive statement, but anyway, it's nice to see a formal proof. What is really interesting about the pigeonhole principle is the various ways in which it can be applied. Okay, so it is the applications that are the main interest in the pigeonhole principle. So there are numerous applications, okay, and sometimes we have to sort of really think hard and be a bit clever about how we set up the situation and use the pigeonhole principle. So let's start with some easy applications, and then we'll slowly proceed towards the trickier ones. So here's the first and kind of maybe obvious one. Suppose I have a room in which there are imagine I had 367 people. Okay, then consider a room with 367 people. Then there exist two people in the room whose birthday is the same. There exist people in the room with the same birthday. And when I say birthday, I just mean the date and month. Okay, so let's see what is this got to do with the pigeonhole principle. Well, what are the possible birthdays, right? What are the possible dates and months you can have? Well, there are 365 days in a typical year, 366 if you count a leap year. Okay? So let us just imagine. So here's the answer to this question. So suppose I look at what are the possible. So there are 366 different birthdays are possible. I am counting the leap year possibility of February 29, for example. So 366 different birthdays are possible. But I've got 367 people in the room, which means, sort of by the pigeonhole principle again, imagine the boxes are the different possible birthdays. So let's try and put it into the form of the pigeonhole principle. So I start with Jan 1, Jan 2, Jan 3. I imagine I have boxes, one for each possible birthday. I also include Feb 29. So I've got 366 possible boxes. And what I'm going to do now is to look at the people in the room, and I will take a person, I will see what their birthday is, and I will put them into that box. Okay, so maybe the very first person has birthday on Jan 1. There is somebody else whose birthday is, let's say, March 16th. So you put them there. Maybe somebody is December 31. You put them there, and so on. So I'm trying to put these 367 people into their respective birthday box, and there are only 366 different boxes. So by the pigeonhole principle, some two people have to go to the same box. I mean, there exists a box which contains two or more people. Okay, but that's really all I have to prove. I have to somehow find two people in the room whose birthday is this. Okay, so that is the by pigeonhole principle, the very first version. There exists. So I'm going to use that symbol that you've seen for there exists. So there exists a box containing at least two people. And that's the box you're looking at. Those guys have the same birthday. Okay, so this is just a straightforward application of the pigeonhole principle itself. Now, let us look at something that's slightly more non-trivial. So I look at three integers. So let A, B, C be three integers. So remember, integers means positive, negative, or zero. I even allow them to be equal. Some of them, maybe I can take the same integer twice or thrice, even maybe. Some are possibly equal also. Okay, now I don't care. I take any three integers and I look at the sums. So I look at A plus B, B plus C, and C plus A. Okay, I'm going to add the integers and two at a time. So these pairwise sums, that's what you call the pairwise sums of these numbers. Now, the thing that we have to prove or observe is the following, that out of these three pairwise sums, at least one of them is an even number. Okay, so here's the thing that we prove. There's our claim. At least one of these sums, one of these three pairwise sums, is an even number. Okay, and we're going to prove this using the pigeonhole principle. So firstly, before we look at how the pigeonhole principle applies, let's just try to play with some possibilities. So how would we do this? So we're going to try and choose three numbers, and we want to sort of get some feel for why is it that at least one of the three pairwise sums will always end up being even. So let's pick some numbers. So suppose I pick one number as 2, and let's say my second number is 5. So I pick A is 2, B is 5. And let me see what I've got so far. The sum of A and B is 7, which is an odd number. Okay. So is it somehow possible for me to choose my third number? Can I choose it cleverly so that when you look at 2 plus C and 5 plus C, both of those turn out also to be odd numbers. In other words, can I somehow prove that my claim is wrong? Can I cleverly choose C to falsify my claim? So let's see, what would we do? Well, what are the possibilities? This number C that we are going to choose, well, there are only two possibilities. This can either be an odd number or an even number. For example, suppose I choose C to be an even number, say 6. Then observe that 2 and 6, their sum becomes an even. Okay, so maybe that's not good. Let me try and be cleverer. Suppose I choose, instead of 6, I choose an even number. Okay, so let's say, okay, I don't want. Sorry, I choose an odd number. I don't want 6. Instead of 6, let me say I will try 7. That's a possibility. Now observe that if I choose 7, then 7 plus 5 becomes an even. Okay. So no matter what I do, if I choose C to be an odd number, then that plus 5 will become even. If I choose C to be even, then that plus 2 will become. Okay. So it looks like I really can't do much. Okay. Whatever I do, I will be forced to get at least one of the sums to be an even. That is the claim. So let us try and prove this claim. So let's try and do this formally using the pigeonhole principle. So let's set it up like this. We will make one box where we will put the even numbers. We will make another box where we will put the odd numbers. Okay, what does this mean? So now I have got three numbers A, B, and C. These are my objects. Okay, my three given numbers, and these are my boxes. There's one box where I will put the evens and another box where I put the odd numbers. So what I'll do is I will look at this number A. When this number A comes in, I will see where should I place it. If it's even, I will put it here. If it's odd, I will put it there. Okay. So if A is even, put it here. Okay. If A is odd, I place it into this box. Okay. So let's get rid of some of these arrows. This box again. Okay. So this is going to be my my algorithm. Okay. Then similarly, when B comes along, I will see whether it's even or odd. Depending on whatever it is, I will put it into that box. So maybe C was odd. So if C is even or odd, depending on that, I will put it in the box. Okay. So what I have done therefore is I have two boxes and I have three numbers. I put those numbers into their appropriate boxes. So this is one way of placing these numbers into the boxes. But now what does the pigeonhole principle tell me? The pigeonhole principle tells me that no matter how you place them, here is one way of placing them. You must have two or more elements inside a single box. So there exists box out of these two containing two or more elements, meaning at least two objects or two numbers. Okay. Now observe that what does that mean? That says, for example, my even box. At least one of them has two numbers. Okay. So if the even box has two numbers, I don't know, A and B maybe, then their sum, when I add up two even numbers, I get an even number. Okay. Okay, maybe that wasn't what happened. Maybe the odd box contained two numbers, A and C, maybe. Then the sum of those two numbers, A and C, is again an even number. Okay. So there is a box containing two objects. Take that box. So choose two numbers from that box. I mean, there may be all three may be in that box also. So choose two numbers, two objects from that box, and observe that their sum is necessarily even. Okay, because odd plus odd is even plus even is also even. So that is the end of it. Okay, so this is an interesting application of the pigeonhole principle.